So now in this lecture, we are going to reinvestigate another old concept that we've been using that term a lot, but now it's time to reinvestigate it and putting our understanding about limits on top of that. So continuity. What does it mean by having your function being a continuous function? That's the term. So you've heard that somewhere here and there back in your algebra course, and now let's reinvestigate this whole concept, but we're going to be giving our limits understanding on top of that. So continuity of a function. More particularly, we're reinvestigating that concept about continuity. So before calculus, then anytime we're defining or anytime we're communicating with anybody else or doing math with us, then we're talking about a continuous function. Then what it is, what it meant back then to be a continuous function, the only way to explain back then is that you're going to have to pull out a graph and you're going to explain your function is a continuous function if you're tracing along the graph. And it's going to give, if tracing along the graph, if you can trace along the graph of the function without lifting the pencil, that graphical explanation has never been wrong. And if I was teaching an algebra class, I would be explaining the exact same way. That explanation is perfectly right. But now, when we're now at calculus level, when we get to calculus, we want to have a closer look, a deeper look in terms of what it means by being able to trace along the graph without lifting the pencil. I mean, why we're bringing up that? I mean, why do we even bring up about lifting a pencil? Is there an instant that we have to lift the pencil? See, instance like this. The graph could go to a point, and then you have to lift your pencil to jump to another piece at a certain break point, x equals a, and then jump to another piece and continue drawing. So an illustration like this is indicating that the function is not continuous at particularly x equals a. So physically tracing along the graph, then you are required to lift your pencil in order to make your way to the other piece. Or in another case of demonstration here, think about what we have seen earlier in earlier lecture, that sometimes our function has vertical asymptote. We can have our function getting close to a line asymptotically, and then we need to lift our pencil to draw the other piece on the other side of that vertical asymptote. And so something like this, once again, the function has a jump, or now informal term being discontinuous at x equals a, because right when it hits x equals a, we definitely have to lift the pencil and change that to the other piece. And so now I blending with our understanding of limits on top of that, let's now give a formal understanding of what it means by being a function continuous at a point here. All right, so now allow me to write down my own definition for being a continuous function. And it's quite a standard definition as well. So I'm going to say any function, or a function f of x is said to be, and now let me highlight the term I'm about to say here in red ink. So a function f of x is said to be continuous at a given point x equals a if it satisfies all of the following. So anyone following with this video of mine, make sure you take note carefully, because the way how I'm organized these requirements right here. So any function f of x, it's set to be continuous at a point x equals a. If it satisfies, now underline this term for me, it needs to satisfy all of the following requirements I'm about to write right here. So requirements number 1. If we're substituting the value x equals a into the function, f of a has to be a defined value, meaning we can substitute, we can plug x equals a into the function and get a value. And that's what it means by requirements number 1, f of a is defined, meaning having a calculated value successfully. Then requirement number 2, the function f of x has a limit as x comes to a, generally from both sides. And that limit here must be an existing limit. So, in other words, saying the limit of this function as x coming close to a exists as a finite value. Going to infinity is not accepted. And then requirement number 3 here. So, and that's the reason why I said we are reinvestigating the entire concept of continuity, but now we blend our understanding of limits on top of that. And now, after successfully passing these two requirements, 1 and 2 right here, the third requirement is that the limit of the function f of x as x comes to a, that finite existing limit must also be equal to the function value at a. And that last requirement here really determines what it means by being continuous at the given point x equals a. And so the first thing you have to keep in mind, anyone after reading this definition must keep in mind, is that in order to say the function is continuous at x equals a, your function must satisfy all of these 3 requirements. Failing one is not going to get that through the door. And through the door, I mean, it's not going to be continuous if you fail one of these 3 requirements. And now I actually wrote down these requirements with the order being as right here. Number 1, f of a has to be defined. It's a defined value. And then number 2, the limit exists. And number 3. So intentionally, this order does mean something. Logically speaking, we need to have the function being defined at the value and the function is having a limit existing before you can check whether the limit equals value with the function value at f of a. And so now the first 2 requirements here can be interchangeable a little bit. So when you're actually doing a problem, then checking to see whether your function is being defined at the value or checking to see if you have a limit existing, either one of these steps can be interchanged, meaning whichever one between these 2 can be done first, that's okay. But checking for that last requirement where limit equals to the function value has to always be the last one. Okay, but so much explanation is nothing compared with doing a live example, an actual example here. So allow me to start getting into an example, and you will understand exactly what I meant by all this definition here. So let's look at our first example here. Example 1. And the instruction of this example says, let's determine if f of x is continuous at the given value x equals a. Okay, and so I'm starting out with our first problem. How about let f of x be the function here is x squared minus 2x plus 3. And the given value here, we want to determine whether the function is continuous. At this point, x equals 1. So at x equals 1. Okay, so the starting step again. First responsibility, we have to check f of 1. Directly substitute that value into the function and find out whether this value, the overall function value, is going to be a defined value, meaning a value that we can actually calculate. Or another way of saying, can we substitute the value in and get a value for output? Yes, we can. There's nothing wrong with this kind of function when we substitute x equals 1 into the function, simply because it's only a simple quadratic function. And so the operation here is allowing us to, we can square 1 minus 2 times 1 plus 3. And all of the mathematical operations being involved in this function has no problem for us, produced no problems for us to substitute 1 into the function. And so 1 squared minus 2 plus 3, so that gives us a 0 value. I mean, sorry for my miscalculation, but that is a positive 2. But having a final output successfully calculated here, it only means we have our function here is defined. So now I'm put a check mark right there, meaning first requirement has been satisfied. So now, satisfying only the first requirements, then we need to move on to the next requirement. So for the next requirement, let's consider what about the limits. So for the function x squared minus 2x plus 3, and this is a good place for anyone viewing this video to apply your understanding or your techniques to find a limit for a function like this. So go ahead and pause the video and find your own limits on this function right here. And tell me whether we can have a successful limit or an existing finite limit here. And this is requirement number 2. We're about to find out whether we have that requirement number 2 successfully satisfied. So indeed, at this point, assuming you took your own step, then, and that's my dots here is indicating that I can leave that for you to take your own steps. And my final limits here also applying my basic limit laws, we also come to limit 2. So that means now looking back into our definition again, our definition of continuity of a function at a point, then requirement number 2, we just now passed requirement number 2 for our function in our current example. And then again, back to the board that we're currently working with the problem, think again that, you see, I could have also started out by checking for this limits before finding out whether the function is defined, because really these two words right here can be independent from each other. And so the order that I wrote in the definition, I said this is 1 and this is 2, but they're not that strictly in this order. These two steps right here we can violate, we can interchange them. But now the last step, now after successfully passing the two requirements, we have a limit, a finite limits here. Now we can check the limits of the function at this value, this given value, as well as the function value being evaluated here. Aren't these two limits agreeing with each other? Yes, they are. So ultimately we came to another observation. So step 3 right here, requirements number 3. So now limits of this function f of x that we're currently working with, as we're allowing x getting close to 1, turns out to be, so it was 2, it turns out to be also the same with the function value at 1. And so now requirements number 3 is just now passed for this function. And once again, let me switch back to the other board so that you can see. So after passing requirements 1 and 2, then we need to move on to requirement 3 and start comparing the two results. Once they met this requirement, meaning the limits of the function as x getting close to a equal the function value at a, which is what's satisfied here in our function. Then now after passing all 3 requirements, now we are ready to make a final conclusion for this function. Allow me to erase this work here and make our ultimate decision. So now we determine that f of x, our final conclusion, f of x is continuous at specifically given point x equals 1. And that is our final answer for this particular problem. And so now let's look at our next problem. So in example 1 again, problem B, let's say we are looking at our function f of x equals x squared minus 9 over x plus 3. And we want to find out, we want to determine whether f of x is continuous at the given point x equals negative 3. Okay? And so this time, let me bring the two boards together so that you can keep having that. We can keep having that. The definition of all the requirements for being continuous is here, listed here, and let's apply that live into our current problem here. So now, if you look at the 3 requirements that I'm listing here, then there is no way to have this equality if any one of these fails. And so, or in other words, in other words, as long as one of these requirements here fails, then automatically the bottom requirements, the very last requirements here will fail as well. So in that way, keep that logic in mind. Let's have a look at this function right here. So just for some fun of doing math right here, how about, and like I said earlier, these first 2 requirements are not really in that strict order, so you can start out by considering a limit first. But having that requirements passed for whatever reason, you still need to make sure you check with the other requirements. And if both of these requirements pass, then we need to move on to the third requirement. Okay? And so, and it's a good place again to apply your limit techniques or your techniques that you've learned in terms of finding limits. So for some good fun of this math problem, how about x squared minus 9 over 3, I'm going to consider the limits problem. Let's find limits as x comes to negative 3. And so once again, I can leave the steps here for you. I have a hint for starting out. We can do a factoring, difference of 2 squares. We can factor out into x minus 3 times x plus 3 over x plus 3. And find out limits. The good usefulness of doing this is that we can cancel out the common factor x plus 3 away, and then once you cancel away that common factor, then you're going to be in a safe zone to start plugging values in, just like usual. And so this limits here, I'm leaving the steps for you, but final answer for that. And once again, if you're feeling like I'm a little too rushed for For you to catch up, go ahead and pause my video and work out on your own steps to find the final limit. But this function here will have a final limit being -6. So we do have a finite existing limits for this. So requirement number 2 is passed, even though I started it out first, because like I said, what I wrote on the board about the 3 requirements, really the first 2 shouldn't matter with their order. Okay, but now if we check after we passed one of the first 2 requirements here, then let's check with the other requirements of the first 2. So, but now really for this function, can we substitute -3 into the function? Just simply substitute. So substituting -3 into the function, we are going to end up with -3 r squared minus 9 divided by -3 plus 3, and this is undefined in math term. Here we have an undefined value. We don't know what value this is. And so having an undefined value right here, then we are violating that first requirements. The first requirement needs us to have a function, our function value defined at x equals a when we substitute or when we plug x equals a into our function. But now in our case, f of -3 is undefined. And so right now we fail the requirements number 1. And that means no need to move on to the third requirement, because as long as one of the first 2 requirements fails, definitely it won't even be solid. It won't even be true to have the third requirement satisfied. And so now you can make your final conclusion. So I don't need to step into the third requirement. I can just now make my final conclusion. Allow me to erase the board here. But f of x is not continuous, okay, at x equals -3. So not continuous is one way of saying it. And so after example B, question B of our current example 1 right here, then you can immediately understand that our function is not continuous at a given point as long as anytime we fail either one of the requirements indicated on the other board there. But now not continuous, we want to come up with a convenient term right here. So not continuous is the same as, sometimes we use that term, a lot of time we use this term, discontinuous. Okay, so we can simply say that the function f of x is discontinuous. This term right here can be regarded as discontinuous at x equals -3. And now let's look at another problem in our example 1. So let's call that part C of example 1. How about we have a function being defined as following. Our function f of x equals x squared for values of x that are less than 0. And this same function f of x will equal minus x plus 2 for values of x greater than or equal to 0. And so this is a piecewise function. Yes, that's what it is. We want to determine whether the function is continuous or discontinuous in the new term we just now learned at x equals 0. And so algebraically speaking, this function, let's find out whether it's defined or undefined at x equals 0. So substituting x equals 0 into the function. Now, we algebraically learn how to evaluate function value for a piecewise function like this. Now, notice when x equals 0, it falls into this other category of the function. So we have to use this bottom piece of the function and substitute 0 in there. But so in the end, we do have a final value being a defined output value, minus 0 plus 2. And that is equals 2. So we have a defined value for f at 0, or in other words, f at 0 is defined. So being defined, and let's now put a check here. Now I am going to move to my other board and allow me to erase the definition of continuity, because I've left it here long enough on the board. And now I'm going to use all that space here to continue working on my big problem here. But so now we are ready for moving on to step 2 right here. Requirements number 2. And now I don't even think that we need to write down requirements 1 and requirement 2. This limit, let's find out what that limit is. The limit of the function. We want to consider the limit when x coming close to 0. But now, finding this limit, we do need to tear it down to a left-hand side limit and a right-hand side limit. So, from the left-hand side, when we let x get close to 0, from the left-hand side, our limits problem will turn into, now remind yourself, when x is getting close to 0 from the left-hand side, that means the values of x have to be less than 0 to the left-hand side of 0. And so that means, let me put the picture up there. Okay, so that means we have to use this piece of function for those x to the left-hand side of 0. And so that means here, back to our function, we're looking at taking limits of x squared function for, as we're letting x come close to 0 from the left-hand side. And limit laws that we have learned now telling us that this limit is 0. From the left-hand side, our function comes to limit 0 when x gets close to 0 from the left-hand side. But we also need to consider finding the limit of this same function f of x, as we're letting x coming close to 0 but from the right-hand side. Now, so coming to 0, this limit point from the right-hand side means, back to our function definitions right here, then we're looking at considering f of x equals this piece of expression right here, minus x plus 2, when we're getting close to 0 from the right-hand side, because to the right-hand side of 0 means those x values are positive, greater than 0. And that means we can re-express our limits problem as finding limits of the function minus x plus 2 as x is getting close to 0 from the right-hand side. And now limit laws again allow me to quickly find out that my limit here overall is going to be positive 2. And so now, at this point, left-hand side limit came to 0. But approaching 0 from the right-hand side came to 2. The two-sided limits just simply do not agree. So from what we've learned regarding limits from both sides, then now our ultimate conclusion here, we can make an ultimate conclusion that for this function f of x, the limits of f of x as x getting close to 0, but generally from both sides, this limit is a DNE. And so, of course, for anyone viewing this video, I'm assuming that you guys, any of you viewing this video is a beginner into this work. So I took a lot of time breaking these problems down in steps right here, but one day when you're fluent enough, trust me, these steps are taking you less than 30 seconds. But so you have now a non-existing limit for your function as x coming close to that limit point. Non-existing limits. What it means now is that we failed requirement number 2. Okay? Remind yourself that we need the function, the limits of this function f of x as x coming to a must exist, okay, as a finite value. But what does our result here say? Does not exist. That means we failed this requirement number 2. So we passed requirement number 1. For requirement number 1, we passed. But for the requirement number 2, we didn't. Requirement number 2, we came all the way down to this, and we failed. And so now, without the need to move on to third requirement, because this limit already failed, or like I said earlier, as I said earlier, one of the 2 requirements before requirement number 3 fails, then automatically you can make this ultimate conclusion. F of x is, now in a new term that we have now learned, f of x is discontinuous. At x equals 0. That is our final answer for this particular problem. All right, so let's now one by one give a graphical explanation of each of our example problem that we've just finished in example 1. And so, starting with example 1, problem A right here, our function was f of x equals x squared minus 2x plus 3, and at given point x equals 1. And so, let me now quickly show everybody, anyone viewing this video, the graph of our function there. So, this is the graph for x squared minus 2x plus 3 right here. And so, at x equals 1, we did earlier through the steps that we had a function value, a function output value defined. So that's the reason why I can have an actual solid point on the graph. And by the way, the graph of this function is being graphed in red color right here. Okay, and so at x equals 1, which is where this vertical line is at, but we do have a solid point on the graph. So that's how I said earlier that we had f of x being defined at this point, x equals 1. And now we moved on to our second requirement. So second requirement, we were looking at the limit. So from the left hand side and from the right hand side, and of course when I was showing the steps, that I was doing it more like the algebra steps, but graphically speaking it's the same. It should be giving the same result, but the function output or the function height in green here does seem to approach to that height being 2. So function output is at 2, and the limit of the function also approaches 2 as we getting close to x equals 1 on the x-axis. And then that is the reason why the function here is continuous. And in the end, it's a parabola. The graph here is a parabola, and it was any parabola or any quadratic function is famously known to be continuous everywhere. So now what we found throughout this example is consistent with what we have learned back in algebra. For our next problem in the example, the function there was in part B, f of x we had was x squared minus 9 over x plus 3. And so, and the value given was at x equals negative 3. And so this function, now allow me to show the graph. All right, so what a surprise to actually see the graph of our function like this, even though it involves some square in there. But yes, in the end, it did turn out to be just a linear line. But since we cannot substitute, remind yourself that we cannot substitute x equals -3 into the function, because it will have a 0 value in the denominator. So failing to substitute the value into the denominator there, then this is the reason why we're having even though being a linear line anywhere outside of that value x equals -3, and when it's x equals -3, we have an empty point right there, a hole on the graph right at x equals -3. So that's indicating and based on our understanding from the algebra courses, that we have an undefined point right there. But then anywhere else outside of x equals -3, then it's reduced into a linear function, x minus 3 right there. Okay, and then so in that way, now when we're taking limits from the left, limits from the right, so taking limits, it agrees with with our result when we calculated earlier through the limits laws, that the limits of this function comes to -6 vertically. So this function had a limit, but did not have the function output value defined at x equals -3. And that is the reason why we said that our function is discontinuous. And so just simply look at the way how the function itself, look at the way how it is for the function. See, if we trace along the graph here, we have to lift our pencil to make our way to the other piece and continue to trace. Otherwise, there's no way to trace along this graph without lifting our pencil, because due to that empty hole right here. All right, so that's a graphical illustration of how to see how it's consistent with what we found earlier, that this function is discontinuous at x equals -3. All right, and now for our problem, the third problem, or problem C of our example 1 right here. Then this was how the function is being defined. So f of x equals x squared for x is being less than 0, and f of x is defined as another piece minus x plus 2 if x is greater than or equal to 0. So this is a piecewise function. So let's look at the graph of this piecewise function. And the given point here in this problem is x equals 0. And so the graph here as a piecewise function, then we have our function here for x less than 0 to the negative side, or to the left hand side of the y-axis. Then we're looking at this x squared graph right here, but it will stop right here when x equals 0. And then when x is greater than 0, then we're looking at the line minus x plus 2. But unfortunately, this line only starts as x equals 0. So, and we have a solid point here when x equals 0, but that belongs to this right piece. And then we have an empty hole here, for the left piece being x squared. And so if we now looking at, and let me leave that actual function, written form of the function there. Now if we take the limits, so function value is defined because we have a solid point here. But if we now take the limits from the left hand side goes one way, and limits from the right hand side of this function goes another way. So this is where we had our limits being a DNE, which means we have a non-existing limit according to our calculation earlier. And graphically, the graph here the graph is showing that we're having two-sided limits disagreeing with each other. And so in that way, requirement number 2 fails in a sense that we have a non-existing limit when x comes close to 0 from both sides. So this is another example where we have our function is having a discontinuity at x equals 0, the given point x equals 0. Because once again, if we are trying or attempting to trace along the graph from the left to the right, but when we hit to x equals 0, we have to lift the pencil to move on to the other piece.